Hi friends, in this video we are going to discuss about electrical brakings. Generally, in our DC machine, we have three types of brakings. One is called dynamic braking, or this is also called rheostatic braking. And next one is plugging, and next one is regenerative braking. Like that, we have three types of brakings in our DC machine. In that, the first one is dynamic braking or rheostatic braking. Let's see what is dynamic braking, how we can brake the motor. For example, first I am going to see DC shunt motor. In DC shunt motor, I am going to brake by using this method. See, actually, this is my DC shunt motor. Is like this. This is my DC shunt motor. That's why it absorbs the armature current. Of course, the shunt current is like this, which is rotating at rated speed. Now, I want to stop my motor. Of course, here we have a armature resistance and the back EMF like this. So how we can stop the motor? In that, we have first method, dynamic braking or rheostatic braking. In this method, the armature disconnected from the supply. Listen carefully, only the armature disconnected from the supply and connected to a rheostat, which is called braking resistance. This is a variable resistance. This is a rheostat. This is the dynamic braking method or rheostatic braking method. In this method, the armature disconnected from the supply and connected to a braking resistance RB. Generally, we know the torque is directly proportional to phi Ia. We want to rotate the rotor in reverse direction from 1000. For example, rated speed is 1000. From 1000, 900, 800, 200, 100 and 0. So to that, we have to opposite direction. That's why we have to oppose the torque. For that, I told you already, either flux direction or armature current direction we have to reverse. For that, here the flux direction is same because the ISH direction is same. But once observe here, my armature disconnected. In this condition, what happened at this condition? My EB act as a source voltage and RB act as a load resistance. Then the armature current flows from EB to RB. This is called the braking armature current. Now this is my braking armature current. Nothing but actually it should take the armature current, but now this is act as a generator which is delivering the armature current. So the armature current is reversed, but that is called braking armature current, and this is called the braking torque. So braking torque is reversed, then automatically the speed also reversed, then automatically it goes to zero speed when our EB is equals to 0, or when our braking current is equals to 0, then our speed also goes to 0. When this total power is dissipated in the braking resistance, then this total power is 0. At that condition, the speed comes to 0. This is what is the dynamic braking? Nothing but when our IAB is equals to 0, then our torque is equals to 0. When the torque is equals to 0 and speed is equals to 0, this is the process in dynamic braking or rheostatic braking. Are you getting or not? Now, here the motor acts as a generator and the current flows from EB to the RB. Nothing but the armature current, braking armature current is flows in reverse direction, then torque reversed and the speed reversed, then it goes to 0 when IAB is equals to 0. Now I want, what is my armature current at braking condition? Can you tell me? What is this armature current? The voltage by resistance, nothing but voltage is the EB and the resistance is the RA plus RB. This is the braking armature current in our dynamic braking method. Is it clear? So this is the dynamic braking condition for shunt motor. And draw the graph. Actually, see here, for example, this is a graph. I'm going to draw the graph in between speed and the armature current, or speed and the torque. Let's take the speed and the torque. Anything? What is the speed, sir? Actually the shunt motor speed in normal direction like this. Actually the shunt motor in reverse motoring, the speed is like this actually. But when the braking is applied, what happens, sir? When the braking is applied, the speeds are like this. This is for braking resistance 1. If the braking resistance increases like that, RB2, these are the conditions. Here, when my torque is equals to 0, this is the torque or current. When the torque is equals to 0, then speed also 0 for dynamic braking. This is important. In dynamic braking, when the torque is equals to 0, then speed is also 0. This is the dynamic braking for DC shunt motor. Sir, what is the dynamic braking process for DC series motor? Let's see. Okay, is it understood? Right? Let's go for DC series motor. This is somewhat different. Let's see. I'm going to draw for DC series motor, the dynamic braking for DC series motor. Let's see. DC series motor. How it is? See, actually the series motor is like this. This is my DC series motor actually. But I want to disconnect the armature from the supply and connect it to a braking resistance or rheostat RB. This is simply the dynamic braking actually. But when this condition, again EB act as a source voltage and RB act as a load, then armature current is reversed. Up to now in this direction, now my armature current is reversed. When the armature current is reversed, nothing but the flux also reversed because the current flows through the field winding only. So if both are reversed, this is only minus of minus plus. So it should not reverse. So what I do, it should not reverse. For that, what should I do? Just very simple, reverse the field winding terminals also. In DC series motor, the armature disconnected from the supply and connected to braking resistance, and field winding terminals also reversed. Terminals also reversed, then only the braking will operate, because now the flux is same. Because see, again the current flows in the same direction in field winding, so flux is same. This is reverse, and then comes to 0. This is generally what is the dynamic braking in DC series motor. What is the armature current at this condition? EB by RA plus RSE plus RB. This is the armature current at this condition. Even the every process is same for motor of shunt and series. Now, what are the characteristics? Actually, these are for shunt motor, right? So, what are the characteristics for series motor? Let's see here. This is for torque and the speed. Actually, at this condition, The DC series motor characteristics are like these. In normal condition, motoring and reverse motoring. But at braking condition, the characteristics are like this. Whenever torque is equals to 0, at that condition, our speed also 0. This is generally motoring, reverse motoring, generating, reverse generating. Here the motor acts as a generator. The dynamic braking or rheostatic braking is same for shunt motor and series motor. Only one difference is that we have to change the field winding terminals. This is simply about the dynamic braking or rheostatic braking. Is it clear? The first one is clear. Now let's go for second one, right? Let's see what is this. For shunt motor, I'm going to see first of all shunt motor, how the plugging will apply. This is my DC shunt motor actually. Like this, I have DC shunt motor which having armature resistance and the back EMF. Exactly, this is the armature current direction, this is the shunt current direction, this is the line current direction, like this. Now I want to stop this motor, brake this motor. How we can brake? By applying plugging. Plugging is nothing but, see here, the armature terminals are reversed. How? Let's see how we can reverse the armature terminals. Let's see, like this. Here, braking resistance is connected like this, and this is connected here. Just plugging nothing but the armature terminals are reversed. When the armature terminals are reversed, see how my armature current is flowing. My armature current is flowing in reverse direction. That's why this is called reverse current braking. This is called reverse current braking because here my armature current flowing in reverse direction. And see, we know the braking torque is directly proportional to phi minus IAB, and then this is also minus IAB. No need of minus because in reverse direction we know that. So this is simply minus IAB braking torque. When the torque is reversed, automatically speed reversed. When the speed is reversed from 1000 to 0, then after it trying to rotates in reverse direction because the reversing current is always flowing, going on. Of course, even though the speed is 0, here the torque not 0 because the current is not 0. The current is continuously flowing. Even though speed is 0, the torque not 0. Then what I have to do? I have to do that. We have to apply mechanical brakings when speed comes to nearly 0 speed. At that condition, we have to apply mechanical brakings, then we can get 0. What I am saying is that when our speed reaches to nearly 0 point, at that condition, try to apply mechanical brakings. This is very important thing in our machines. What is that? Plugging. Right? So, this is plugging and reverse current braking. Here, what is my armature current at braking? Can you tell me? Tell me, sir. Here, minus plus flowing like this, again minus plus. So, voltage and back EMFs are added. And what is the resistance in this loop? In this loop, the resistance is RA plus RB. So, see here, the voltage content is more. That's why current is more. If the current is more, automatically the braking torque is also more. So nothing but this having the maximum braking torque compared to other braking methods. Which method having the maximum braking torque? This method, the plugging having the maximum braking torque compared to other. This is very important from this one. And here the machine doesn't act as a generator. The motor acts as a motor only. This doesn't act as a generator. This is another thing. Right, sir. Let's draw a graph for this shunt motor. How the graph? See, this is for example torque and the speed. Actually, DC shunt motor speeds are like this for motoring and like this for reverse motoring. But when applied the braking, then the characteristics are like this. This is for RB1 and this is for RB2, etc. See here, even though torque is 0, but the speed not 0, when the torque is 0, here the positive speed, here the negative speed, the rotor tries to rotate in reverse direction. This is simply about the plugging in shunt motor. Are you getting or not? Now, let's try to draw the same for DC series motor. Let's see how the plugging applied for DC series motor. Once analyze here. So, let's take here DC series motor. Actually, the series motor is like this. This is my DC series motor. Now I have to apply the plugging. So plugging nothing but we have to reverse the armature terminals. That's it. Here I am going to reverse my armature terminals. Then the armature current is reversed. When the armature current is reversed, torque reversed and speed comes to 0. Then after goes in negative direction. Then we have to apply mechanical brakings. Everything is similar. And in this method, what are the characteristics for series motor? Let's see here. See, this is a series motor, right? What are the speed torque characteristics for series motor? We know the speed characteristics are like this in normal motoring and reverse motoring. But when we are going for plugging in braking condition, the speed characteristics are like this. Here, even though the torque is 0, the speed not 0, it goes from positive to negative. This is the plugging or reverse current braking, the second method, which having the maximum torque. And in generally they will ask you question on this formula. IAB is equals to EB plus V upon RA plus RB for shunt, and for series RSE is added. This is very important and which having the maximum braking torque compared to all other methods. Right? Are you clear? Right, sir. So first one is dynamic braking or rheostatic braking. Second one is plugging. Sir, what is the third one? Can you tell me what is the third one? Very good. The third one is the regenerative braking. This is also important. Regenerative. The name itself indicates that during the braking condition, it will regenerate around 60 to 70% of power fed back to the supply. This is the major advantage of regenerative braking. Generally in trains you can see this is regenerative method, regenerative connected. In lifts you can see regenerative connected. In the lift they will paste that like a small board like that. So regeneration will take place. Sir, how it will take place? Before that, what are the conditions to apply the regenerative braking? The conditions are, first one, it should operate at overhauling load. This is must and should, first thing. Nothing but the speed of the motor is very greater than no load speed actually. The speed should be very high. That is overhauling load. Sir, when it is possible, in generally downstream of vehicles. Downstream of vehicles and trains and lifts. Downstream of lifts, the speed is maximum, yes or no? At that condition only we can apply regenerative braking. Otherwise we cannot apply regenerative braking. This is the first condition. And what is the second condition? The back EMF of the motor should be greater than the supply voltage. This is difficult thing, right? In generally, always back EMF is more. That's why in motor, supply to the armature current will flow. That's why it is motor. But what I am saying here, the back EMF is greater than the V. See, for example, I am taking a shunt motor. For example, this is my shunt motor, actually V, and this is actually our armature, which having the back EMF here. So generally motor nothing but it should supply the current like this. But what I am telling is that here back EMF is greater than the supply voltage. If back EMF is greater than the supply voltage, then the current flows from back EMF to the supply voltage. Nothing but the motor acts as a generator in this case, and in dynamic case motor acts as a generator. This is not motor now in regenerative braking. Regenerative nothing but it is act as a generator. Are you clear? Are you okay? Right, sir. So tell me, sir, in this condition how? Simply see here, that is what regenerative braking. Here in this condition it will give the supply reverse to the source. And in generally the regenerative braking method not to have zero, just to reduce the speed below the no load speed only. In this method we can't get zero speed, just this is used to reduce the speed from above rated speed to the below rated speed, below no load speed only. Only for that, at this condition again EB is less than V. When the speed is less than no load speed and EB is less than V, then the machine acts as a again motor, then the generation is completed. This is what the regenerative braking for shunt motor, and these conditions are important. And next one, what about series motor, sir? The question very important. In which of the following motor we cannot apply regenerative braking directly? We cannot apply regenerative braking directly for DC series motor. Don't say can't apply, because we are applying in lifts, we are applying in traction, we are applying in vehicles, we are applying in cranes. But directly this is not possible, because the greater than the no load speed. Is it possible? What is the no load speed of DC series motor? Infinite. Greater than infinite. Are you mad? Yes or no? So here the very difficult to apply the regenerative braking, but we can apply regenerative braking by adding extra auxiliary set of windings, in series to the field winding like this. Then we can apply regenerative braking for DC series motor too. But we cannot apply regenerative braking directly for DC series motor. Remember this point. Is it okay or not? Right, sir? So this is simply about the regenerative braking for DC motors. Are you clear? Right, sir? Right, sir. So generally the electrical brakings for DC motors we completed. Actually the same are we have for induction machines also. Even induction machines also, we have three types of braking methods. One is the dynamic braking, as usually. Next one is the plugging, in generally, and next one is the regenerative braking. Of course, that is in generally somewhat difficult thing. Let's see this dynamic and plugging. How we can apply dynamic braking for three-phase induction motor? How we can apply, sir? Very simple. Just I said you what? Disconnect the supply from the armature, disconnected from the supply for DC motor. Here also disconnect the three-phase supply and just give a DC supply. Just give a small DC supply, then the dynamic braking will apply here. Actually, we have three-phase supply, but disconnect the three-phase supply and apply a small DC supply. Then dynamic braking will apply for induction motor. What about plugging? Can you tell me? Actually, this is like this. Three-phase AC supply given to the induction motor, but for plugging, reverse the phase sequence. Phase sequence reverse nothing but any two phases reversed, then phase sequence reversed. Yes or no? RYB actually. RYB actually. Reversing nothing but R is the same, but BY reversed. Nothing but RBY. Actually, this is positive, this is negative. So, like this, by changing the phase sequence, we can apply plugging. If the speed is more than NR, if the speed is greater than NS, then that is regenerative braking applied in general thing. If NR is less than NS, motor, NR is greater than NS, generator, it's normal thing. Yes or no? So that's why for induction machine also the braking methods are same. These are in generally very important for traction. Especially they will ask you question in traction only. Sometimes they are asking question like this. Generally, I said you, in traction, which motor is preferable? In traction, we are using DC series motor. Very good question. How many DC series motors are you are using? For example, n number of DC series motors I am using, for example. Okay? Are you ready? So, n number of DC series motor connected in series or parallel? Tell me. Can you give me the answer? Of course, we are using DC series motors. Okay. This DC series motor connected in series or parallel, which is better? Let's check it. For example, I take in two DC series motors. Those two DC series motors are connected in series like this. See, this is connected to the supply voltage, constant supply voltage, which giving the current. This is the current of IA here. Of course, this is the current of IA because both are in series. At this condition, generally we know the torque is directly proportional to IA square. Yes or no? When the torque is directly proportional to IA square, then the series torque is directly proportional to IA square. Then the series torque is equals to some K times of IA square. Just remember this. Are you okay? Next, to take the two DC series motors in parallel. For example, now I am taking the same two DC series motors which are connected in parallel. Let's see. Here my armature current, actually the current, this is the current I, but here the current is I by 2 and here the current is I by 2. For example, take here current I for easy analysis. So let's tell me, here also the torque is directly proportional to I square actually. But here the torque is directly proportional to what is the current through your armature? I by 2 whole square for parallel connection. Let's tell me what is parallel connection is equals to. What is that? Is directly proportional to 1 by 2 square into I square. So the TP is equals to 1 by 2, so some K into 1 by 2 square into I square. This is for parallel and this is for series. Now tell me, which having maximum torque? So let's see, substitute this Ki square. Ki square is nothing but TSE. So the torque in parallel connection is equals to 1 by 2 whole square of Ki square. Ki square nothing but the torque in series connection, nothing but the torque in parallel of 4 is equals to torque in series, nothing but in series connection the torque is 4 times of the parallel connection. Are you getting or not? Because here we are using only 2 motors. That's why the torque in series connection is equals to 2 square times of the torque in parallel connection. If you are using n motors, the torque in series connection is equals to n square times of the torque in parallel connection. So tell me, which is more preferable, series connection or parallel connection? Sir, are you mad? Here in series connection, the torque is maximum, sir. If you are using 10 motors, the torque in series connection is equals to 100 times of the torque in parallel connection. Then I have to go for parallel connection. I mustn't use the series connection only. So in traction, we have to use DC series motors connected in series. Are you concluded that? Just wait for 2 minutes. Then after conclude, what is your answer? Let's see here. Of course, we know this. Now, we know the P is equals to NT, the power. Yes or no? So, the P is equals to NT. Here, the torque is the given like this. Are you okay? What is the speed? What is the speed? I said that the power is constant for series and parallel connection. So the power in parallel connection is equals to power in series connection. What is the power in parallel connection? Speed in parallel connection and torque in parallel connection is equals to the speed in series connection and torque in series connection. So let's see the speed in parallel connection by speed in series connection is equals to the speed in the torque in series connection, nothing but n square TP by TP. TP gets cancelled. So the speed in parallel connection is equals to n square times of the speed in series connection. Are you getting or not? What I said that here the torque they given like this. Torque in series is equals to n square times of the torque in parallel. Let's see, P is equals to NT. Actually, the power in series connection is equals to parallel connection. So, power in series connection is equals to parallel connection. Power nothing but NT. N, okay, N by N is equals to T by T. TSC nothing but N square of TP by TP gets cancelled. Or let's do in simple manner also, the torque in series connection is equals to N square times of torque in parallel connection. We know P is equals to NT, so T is equals to P by N, nothing but the power in series connection by the speed in series connection is equals to N square times of the power in parallel connection by the speed in parallel connection. Whatever the power is same for series and parallel, now the speed in parallel connection is equals to N square times of the speed in series connection. This is our topic. So what you observed here? What you observed here, the speed in parallel connection is 100 times of the speed in series connection. Now tell me, which is preferable? Series connection or parallel connection? Yeah, now you have an idea. Which is preferable? At starting, the DC series motor should be connected in series for high starting torque, but at running condition, the number of DC series motors should be connected in parallel for high speed. So, what is the connection in traction? In traction, the connection is series paralleling. What I am saying that in traction, DC series motors are connected in series paralleling, because in series the torque is n square times of the parallel, and in parallel the speed is n square times of the series. That's why at starting we must require a high starting torque. That's why at starting this series motor should be connected in series to get the high starting torque, and at running we must have a high speed. That's why at running the number of series motors should be connected in parallel. That's why it is called series paralleling. Series paralleling connection is preferable. This is simply about the small concept in traction. Are you okay? Getting or not? Right? Thank you.